Hi everyone. In today's video, I am going to cover this paper titled When Does Metadata Conditioning Not Work for Language Model Pre-training? A study with context-free grammars by people from the University of Tokyo, Riken AIP, as well as UC Berkeley, Preferred Networks, and I think I've covered everything. The lead authors are Rei Hibuchi, Ryotaro Kawata, and Naoki Nishikawa. I'm really sorry if I mispronounced any of those names. This is a paper from Code 2025. Code is a new conference. If you're not familiar with it, this is the second edition. I have been covering, I guess I haven't uploaded any yet, but I've covered two papers in a similar vein: metadata conditioning accelerates LLM pre-training, as well as URL's help topics guide. And in general, I want to cover more about this line of work because I find it interesting. All right, let's dive right into it. The ability to acquire latent semantics is one of the key properties that determines the performance of language models. One convenient approach to invoke this ability is to pre-print metadata at the beginning of text and pre-training, making it easier for the model to access latent semantics before observing the entire text. Previous studies have reported that this technique actually improves the performance of trained models in downstream tasks. However, this improvement has been observed only in specific downstream tasks without consistent enhancement in average next token prediction loss. All right. So this is seen in past papers. To understand this phenomenon, we closely investigate how reprinting metadata during pre-training affects model performance by examining its behavior using artificial data. Interestingly, we found that this approach produces both positive and negative effects. We demonstrate that the effectiveness of the approach depends on whether latent semantics can be inferred from the downstream task's prompt. Specifically, through investigations using data generated by probabilistic context-free grammars, we show that training with metadata helps improve model performance when the given context is long enough to infer latent semantics. I think this is a common thing that have been present in the past two papers. Uh, so the follow-ups to the original Miko work show that you only get performance gains when you're evaluating with long prompts and not with short prompts. I suppose this is somewhat related to what they're also claiming. Let's delve right into it. In contrast, the technique negatively impacts performance when the context lacks the necessary information to make an accurate posterior inference. So I think this will be a fairly standard paragraph. Language models do good. Various abilities, data from various sources are used. You have structured and unstructured data, and they vary a lot, right? To better understand the diversity, one important thing is to condition the documents on metadata, and this has been done in a few works. For example, this work, which is the Miko work, reported performance improves. This strategy makes the model accessible to the latent semantics of data without observing entire documents, and one might speculate that invokes the model's ability to better capture these latent semantics. Nevertheless, it remains unclear whether providing metadata serves as a universal solution. Indeed, as reported in this paper, improvements in downstream task performance are not consistent across tasks, and moreover, the addition of metadata does not lead to lower pre-training loss. Despite the attractiveness and opacity of metadata conditioning, tracing how it influences model performance remains challenging due to the complexity of latent semantics. As a result, the community still lacks. Yeah, this is all fair. In this paper, we systematically investigate the impact of pre-printing metadata during pre-training. To avoid the difficulty of analysis caused by real-world data, we conduct experiments on synthetic data with controllable and well-understood metadata. All right, specifically inspired by, okay, this is the physics of LLM paper. They generate synthetic data based on context-free grammar. They generate data using multiple rules and define metadata as the information that indicates which rule was used. And then they investigate how the amount of metadata provided affects the analysis. Really interesting. One of the key findings is that metadata conditioning can negatively affect performance. This is shown in figure 1.1. I'll go to that. As shown in A1, our experimental results reveal that when the task prompt is short, the model trained exhibits lower accuracy in inferring latent semantics compared to the model trained without metadata. This results in reduced performance on downstream tasks. as in A2. On the other hand, as shown in B1, when the task prompt becomes longer, the model trained with metadata becomes capable of inferring latent semantics comparably to model trained without metadata. In this case, the model inferred with metadata demonstrates higher performance in downstream tasks as shown in B2. All right, let's jump to the figure. So this is A1, this is A2, ability to estimate latent semantics, context length. So when the context length is big, you get better performance with metadata, but when it's small, you don't. Similarly, when the downstream task performance shows similar abilities, but I guess this is like hand wave plots and not like, yeah, numerical plots. They must have like looked at numbers to come up with it, but it's not like uh, it's plotting some hard numbers. I think so. We investigate the impact of rebranding metadata during pre-training. They create this data set, they find hidden trade-off, interesting metadata conditioning impairs the model's ability to infer latent semantics from limited context. To provide an understanding of why models trained with metadata fail to infer latent semantics, they introduce a theoretical framework using predictive distributions with respect to latent semantics. Okay, this I don't fully understand, but I guess I will as time goes on. So the top is conceptual illustration of how metadata narrows latent semantics and how it is incorporated into training data. So you can have like a context, uh, attention, subject, verb, object thing like attention filter stimuli, attention outperforms RN, attention drives stimuli, attention drives brand recall. So these are all different texts, and when you add metadata, it can be about language model, advertising, or yeah. Okay, let's look at the dataset construction. They use probabilistic context-free grammar that is systematic and controllable. We extended D-level uh, probabilistic context-free grammar. I think this is the original physical language model, one of those papers by incorporating metadata. I don't know which paper is this. Learning syntax or context, understanding hierarchical generation. Really good. This looks very interesting. Okay, so what is a D-level probabilistic control context-free grammar? We first explain sentence generation using this. A probabilistic context-free grammar is denoted by G, which consists of symbols and production rules. Specifically, we start with a sequence of length 1 consisting of a unique root symbol, and then for I equals 0 to D minus 1, they generate a new sequence of symbols from the previous set. For each production rule, has length of 2 or 3 and consists of rules in the form. So S1 can produce all of these, and or it can also be this. So like the rule is that either S1 goes into S2, S3, S4, or into this with some probability on each. Yeah. At ith step, we replace each symbol in the previous sentence according to the production rule. By repeating this d times, they obtain a sequence of symbols in SD, which they refer to as terminal symbols. For simplicity, the symbols at different levels are assumed to be disjoint. Okay, so it's not like S1 can go into S2 and but also have S1 again or something like that. The distribution generated by a probabilistic context-free grammar is denoted by PG, and its support is denoted by LG. The procedure is this. So this is like this but with in an algorithmic format. So this is a two-level context-free grammar where you start with S, you use a rule 0, 0, you generate A and B, and then you use these rules to generate, yeah, layer 2. Now, D-level probabilistic context-free grammar with hierarchical metadata. Now they introduce the notion of metadata in the context of this. They conceptualize metadata as high-level information underlying the sentence generation process. We operationalize it as a set of meta-level information that modulate the production rule. Specifically, they suppose that there are multiple choices of each production rule at each level. We select one of the rules whose index is corresponded represented by JI. They formally define metadata as a sequence of indices corresponding to the selected production rule. Okay, so which production rules were used essentially? Once a rule is determined, the probabilistic context-free grammar is constructed as G given this indices. We generate the sequence, and now note that different sequence use a different sample. So for different sequences, you'll use different set of production. You'll select different like branches of the tree essentially or graph. In this way, within the probabilistic context grammar, they define metadata as meta information that specifies the choice of rules. Although metadata directly defines the content of the sentence, it constrains the possible sentence structure compared to the full set of rules. This corresponds to how in real-world settings labels such as source, style, or human reference roughly partition the space of plausible sentences. This is really cool. Okay, so how do they generate data? They described how the dataset is generated to investigate how the amount of metadata provided affects the learning of language models. They manipulate the level-wise availability of metadata labels in the probabilistic context grammar. They refer to providing metadata up to depth DM as supplying the partial metadata from the full metadata. Okay, roughly DM quantifies the extent of available metadata, whereas D minus GM represents the range over which the model must navigate without metadata guidance. Makes sense? In practice, this corresponds to controlling the extent of specificity with which sentences are mentioned. Okay, so you basically provide partial information and then the model needs to essentially do the rest. To provide metadata up to depth DM, we prepend DM metadata tokens followed by D minus DM mask tokens to the sentence X sample P of. Uh, so you have DM metadata tokens and then rest are masks, and then you sample based on these rules. The training dataset is constructed by mixing sentences augmented with metadata with equiprobability and sentences prefixed with mask tokens with equal probability. For further details, look into Appendix A. The inference dataset as well as metadata-less training dataset used for comparisons constructed by simply prepending D mask tokens. The purpose of inserting non-informative mask tokens is to maintain constant sequence length so that, mm, okay, so essentially those tokens sort of act like think or pause tokens for prior work, essentially having equal compute usage for both the training processes. Okay, and this looks good so far. Now experiments, they choose the transformer by following yeah, the physics of LM work. They'll use llama 12 layer 12 head row 768. Attention, sorry, hidden size. The data generation process uses probabilistic context grammar with hierarchical level D5. Each is selected from one of two rules with equal probability. Okay, so it's not skewed. Only two candidates per level may appear limited, but each metadata label exponentially narrows down the set of possible grammars. Roughly speaking, full metadata reduces the ambiguity by a factor of 32 compared to metadata free. Therefore, this setup is enough to meaningfully examine the influence. Okay, we compare the results by varying the depth of prepended metadata. When larger depth means richer conditioning, depending using the next token prediction loss. The loss is computed only with terminal symbols and the end of sentence, excluding the beginning and metadata. Therefore, the only difference among training setups is where the metadata is included, and no additional supervision is provided for learning the metadata itself. Training with or without does not affect next token. Okay, a prediction loss. As a preliminary result, they look at the loss performance in figure 3.1. You see all the curves basically overlap. Although our dataset is more complex than that of this paper due to hierarchical branching, the model reduced the loss well. Notably, they find no significant difference in loss between models trained with depth greater than equal to 1 and depth 0, which aligns with the insight from this paper. So I guess the insight that it aligns with is that metadata conditioning does not lead to poor loss, something of that sort. Now, if you look at uh, uh, okay, so this is without metadata. Okay. And this is with metadata, and with metadata you see that the loss and inference is performed on data with uh, prepended metadata, they find that substantial smaller loss. This indicates that model trained with metadata conditioning can be better. And yeah, this contrasts with the case when metadata is not used. So the observation is for average next token prediction loss, metadata conditioning improves performance only when metadata is available at inference time. If metadata is not accessible, no significant improvement is observed. So yeah, this is inference without metadata, but with models, I believe, trained with different amounts of metadata. This is not, yeah. We find no significant difference in loss between models trained with metadata. So at inference time, they hide essentially the metadata and see that if the model does well. But if you really want a model to do well, you need to show it metadata. If it's trained with metadata, to do better with no metadata than no metadata. All right, training with metadata degrades accuracy. Average next token prediction loss provides only a coarse measure of model behavior and fails to capture fine-grained differences. This limitation makes it difficult for previous studies to understand the mechanism of metadata conditioning. Okay, however, our control setup allows a more detailed investigation. To examine how well the trained model can properly infer the latent semantics, they consider probing tasks that predicts the metadata in order to investigate whether a trained model can properly extract the latent semantics. All right. Uh, so let's see how do they probe. Now you have okay L layers and D be the level of the probabilistic context-free grammar rule. So given an input generated from these things, let HLI denote the average of hidden states over 5 consecutive tokens starting from position I at layer L. For each LDI layer L, D is level of the rule, and I is what's I again? Position. They train D distinct linear binary classifiers. The D dashed classifier predicts the metadata this from this. We define metadata probing accuracy at the rate at which all classifiers return the correct label. The hidden state of later tokens generally aggregate information over longer range and thus tend to yield better performance. They evaluate accuracy across various versions I and across different layers to gain a comprehensive view. Alright. And the results are summarized in figure 3.2. Before seeing the results, one might intuitively expect that models trained with metadata conditioning would associate latent semantics with document content, thereby improving metadata probing accuracy. In fact, however, metadata conditioning worsened label probing accuracy. Okay. In particular, when the prompt length is short, the accuracy of models trained with metadata is notably worse than without. When metadata of depth 3 or 5 is prepended, the accuracy at prompt length 5 is around chance level. This indicates that the model trained with metadata cannot infer latent semantics during inference if the prompt provides too little information. Okay, interesting. So what they're essentially saying is that you would expect that if you train with metadata conditioning, the model would start to associate latent semantics with like the string sequences and get like the probing would be better, but they find metadata conditioning reduces label probing accuracy, especially when the prompt is short. In contrast, as the prompt length increases, models trained with metadata become capable of accurately predicting the metadata. Indeed, the large gap seen at prompt 5 largely disappears when you have a prompt length 50 or 100. This suggests that models trained with metadata can extract semantics as long as the sequence is long. So finding if prompt is short, it fails more, and when it becomes longer, it works. This is which figure is this? This is figure 3.2. This is the probing accuracy. They plot a transition with respect to token position. They use a 12th layer, and each column represents corresponds to the depth of the context-free grammar tree. The dth column represents the accuracy of classifying branches up to d minus 1. The chance of correctly predicting the metadata from layer 0 to layer d minus 1 is 1 divided by 2 to the d. Okay. Mm, Sense it's improving when you have longer prompts. Okay. Yeah. Now, 3.3 training with predicted downstream performance. They analyze the effect of metadata conditioning on downstream task performance. Although previous studies report improvement, they do not offer detailed explanation. To gain deeper understanding, they perform sequence generation and employ a metric called grammatical accuracy, which measures how accurate a model generates grammatical sentences. Okay, so how do they measure the accuracy? First, we randomly provide a model with initial part of sequence and evaluate whether it can generate a grammatically correct sequence. So yeah, then they extract the first LP tokens as prompt and let the model generate tokens auto-regressively till it generates end of sentence. Then this is a generated thing, and this ZI is the full thing, prompt plus generated. And then the grammatical accuracy is whether ZI is a correct sequence of grammar G, and they use the CYK algorithm to verify this. Okay, as seen in previous subsection, the performance of models trained with metadata is highly dependent on prompt length. Therefore, this metric uh, the test is across various prompt lengths. Table 3.1 surprisingly seemingly contrary to the old findings show improved performance. Uh, they see that metadata conditioning led to decrease accuracy when the prompt was short. However, as it increases, it becomes better. So as the prompt, yeah, this is like a very noticeable thing. The pattern is reminiscent of finding one model trained with metadata struggle to infer latent semantics from short prompts. On the other hand, when prompts have sufficient information, the metadata condition models achieve lower loss. So the finding is essentially metadata conditioning degrades the downstream task performance if the task prompt is short. This is because models trained with metadata cannot infer latent semantics from the short prompt. On the other hand, for tasks with long prompt, metadata conditioning improves the performance. Pretty cool. All right. So next is the interpretation. So far, I really like how they use context-free grammars to do this. Training with metadata degrades the downstream performance for short prompts. Uh, sorry, yeah, the inference. We compare training with and without metadata in how the models implicitly learn latent semantics. Without metadata, the models need to learn the hierarchical mixture of grammar directly from data, which is challenging. With metadata, grammar inference becomes easier, but the accurate prediction of metadata itself becomes necessary. And this is the trade-off in inference and learning, as per them. So, a framework for latent semantic acquisition via marginalization in the presence or absence of metadata. Okay, this is quite a mouthful, but let's see what they're saying. Training without metadata. We begin by formalizing the role of latent semantics when training is performed without metadata. Given a prompt X, subjective distribution of output Y can be decomposed as the likelihood and the posterior. So this is estimating GL is latent semantics. So you estimate the latent semantics given the prompt, and then you use the estimated latent semantics and the prompt to estimate the output. So this is like very classic estimation of y given x by using like an intermediate state essentially, which is the latent semantics for this. And this is from the principle of marginalization. So y can be generated by sampling a posterior and then using a likelihood function. When trained without providing the metadata j, the model implicitly approximates the likelihood and the posterior. Prediction of this is not trivial even if we know the candidates because we get samples from different hierarchical context-free grammars, and the total support is uh, what is L here? Hmm. I believe it's lost, I guess. It's not super clear what L is. Let me see if they define it. But yeah. Uh, if you train with metadata, you have a metadata J, and then you can decompose it as predicting J given X and then using it to predict Y, which can also be thought of as you are using X and J to predict like latent semantics and using that and X to predict next token. So this is posterior given by J, likelihood, and then this entire thing becomes a likelihood and training with J. Note that this in this setting, these two are equivalent because we do not need to know J once we know the grammar GL because yeah, J and GL are essentially uh, like J is coming from the grammar. Right? So yeah, sampling metadata from its posterior, sampling a probabilistic context-free grammar from its rich posterior metadata, generating Y condition both these things. In this case, the model is focused on task A2 and B because the information of J is provided. Therefore, this is implicitly constructed in the model. As a training data set includes both samples with and without A1 and A2 are launched separately. Okay, makes sense. Understanding trade-offs in metadata conditioning through a formal framework. The proposed framework highlights both positive and negative effects. The advantage of metadata conditioning is that learning the richer posterior metadata is facilitated. However, we obtain the candidate for context-free grammar. Predicting this in A2 becomes much easier than estimating this in A. Yeah, because you have like J as well when you're predicting the grammar. You have some like historical data essentially. The drawback of metadata conditioning is that estimation performance of posterior in A1 deteriorates. When inference is performed without metadata, the posterior of latent semantics degenerates, making it more difficult to capture the latent semantics. So when you have metadata conditioning and you are performing inference without metadata, this prediction, I guess, is like a degenerate thing. These frameworks allow us to interpret previous experimental results as follows. So the observation with metadata conditioning prediction of the symbols, like the J is like the decisions you've made essentially in the tree, is less efficient, but prediction of this is more efficient than without metadata. It implies a trade-off in prediction of the rules given the prompt and the grammar given the prompt and rules chosen. Therefore, the grammar given the prompt and rules chosen. Therefore, the average next token prediction loss remains consistent regardless of whether metadata conditioning is used or not. Okay, I don't see how they make the final leap appropriate, but I can see like there's talking about something like since none is clearly better, you get similar results. Now, in the prediction of finding one, we find that training with metadata prediction of this becomes degenerate in finding one. This negatively affects prediction of GL given X. However, when the task prompt X is significantly rich, predicting this is easy and the negative effect of metadata conditioning becomes small. Ah, okay, which is why long prompts do better. For finding two, when prompt X is limited, it is difficult to predict P of J given X. In this case, the no metadata model predicts P of GL given X more accurately and achieves higher grammatical accuracy. When X is rich, predicting this becomes easier. In this situation, there is no difference between metadata and no metadata setting, as the metadata condition model efficiently predicts the grammar given the rules and given the prompt and the infer scene rules. It can implicitly construct this grammar given the prompt. Therefore, the with metadata setting achieves higher grammatical accuracy. Right? Uh, yeah. So in this case, no metadata more accurately. So essentially everything hinges on the prompt having enough information on. Yeah. Related work when instruction models can follow user instructions, relying solely on instruction leads to ambiguity. So these are works that address this by training models with metadata that encodes attributes such as domain, etc. They also incorporate preference store scores from human judgment as conditioning signals, resulting in reduced toxicity, efficiency, and performance improvement. LLM training methods that incorporate multiple pre-training and post-training stages with diverse forms of labeling have demonstrated improved downstream performance. For example, in this work, they leverage hypertextual structures. Gao et al. Integrate metadata such as URLs, and this work utilize human preference score during pre-training. Zhang et al. Reduced catastrophic forgetting by conditioning a short topic-related hints. Allen and Lee showed that training with special token marking chunk documents enabled the model to allocate its capacity more efficiently. This work demonstrates that tagging the source reliability helps the model acquire implicit meta-learning capabilities. I have not heard of this work, but yeah, this looks very interesting as well. These studies suggest that metadata can enhance not only controllability but also performance. However, such conditioning influences model behavior, particularly when metadata is not used at pre-training but unavailable. Is used at pre-training but unavailable at inference. Our study directly addressed this issue through controlled experiments using probabilistic context-free grammars and revealed that the benefits critically depend on the relationship between data semantics and the information provided by prompt. So conclusion is in this study, they systematically investigate and using context-free grammars. The key finding reveals a trade-off metadata conditioning enhances performance on downstream tasks with sufficiently long task prompt that allow for the prediction of latent semantics, but it degrades performance on tasks with task prompts too short to predict latent semantics. These findings highlight the need for more nuanced approach to metadata conditioning, offering a crucial practical guideline. Simply maximizing metadata is not always beneficial. Instead, strategy should be tailored based on the expected nature of downstream tasks. Conditioning with excessive metadata beyond what is potentially inferable from a typical prompt can be counterproductive or for downstream tasks. And then future work should focus on developing pre-training strategies that mitigate this trade-off based on task complexity. Additionally, exploring the impact of different metadata types will also be helpful. All right, let's look at the appendix. This are the grammar details, and these are the loss values from various positions. Uh, this is change in calibration loss for test data without data with respect to number of returning steps, calibration histogram at the final equation. Okay, yeah. Overall, this is a really cool paper. I really liked how they use formal grammars to sort of break down the problem into like one where you can make conclusive remarks. Yeah, I guess now I have a few more papers in my reading list on this topic, and every paper I read gives me like a few more. So I don't know how long will the cycle last, but yeah, see you guys next time.